Welcome back to Honors Calculus. In this video, we're going to be looking at absolute and relative extrema. We established previously the extreme value theorem, noting that on a closed interval, we are guaranteed to have a maximum and a minimum value occurring. But we didn't have any tools for establishing where that value was going to occur. And so in order to develop those tools, we need to step away from the absolute extrema and look at the relative extrema, which is probably the one you're more familiar with anyway. Let me get my head out of the way and let's dive in. If I look at an arbitrary function, like say this cubic function, we know that if I continue this path out, the function will continue indefinitely. And as x goes to infinity, this particular curve is drawn to go to infinity. As x goes to negative infinity, this particular curve is drawn to go to negative infinity. So on the entire interval, this function doesn't have extreme values on the entire real line. But we do have a peak here, and we do have a trough here. The idea of a relative extrema is a claim that we can cut a window so that the particular point is the extreme value, either the maximum or the minimum on that curve. All right, so putting that in words, we say that x equals a is a relative extreme value of the function if and only if there is some delta bigger than 0, such that f of a is an extreme value, either the maximum or the minimum, on the closed interval a minus delta to a plus delta. So carrying in the definition of absolute extrema, we know that the function has to be continuous on this closed interval. So we're looking only at points where the function is continuous and where there is an interval around the point where the function is continuous. But relative extrema must occur at critical values, is the claim in this theorem. Critical values being places where the derivative is either 0 or undefined. And once again, we're going to prove this looking at the maximum, and I'm going to claim that the minimum proof follows the same idea. If the derivative is undefined, that's all we really need. So we're going to assume that the derivative does in fact exist. And if it has a value, then it is either going to be greater than zero, or less than zero, or equal to zero. So let's look at greater than zero first. And remember the definition of the derivative. We're looking at the limit as delta x goes to zero of f of a plus delta x minus f of a all over delta x. So let's define b equals a plus delta x for some finite larger than 0. And now we have f of b minus f of a over, well, if b is a plus delta x, then delta x itself must be b minus a. And we are taking the limit, but we know that we want this result to be bigger than zero. So this thing itself must be bigger than zero. All right, so because I picked delta x bigger than zero, that means that b is greater than a, which means that f of b is greater than f of a. Which means that f of a is not a maximal. All right. Well, if we pick b equals a plus delta x for delta x being less than zero this time, then we can set this up the same way. And in order for this quotient to be less than zero, they have to have different signs. If delta x is less than zero, remember b minus a is delta x, that's less than zero, which means again that f of b minus f of a must be positive, which means that f of b is greater than f of a, and f of a is not a maximum once again. All right, well, we know that extrema have to exist. We've established that when they exist, the derivative might be undefined. It might be, well, it can't be positive, it can't be negative. The only thing left is equal to zero. And here again, the description of the theorem, the particulars of the statement of the theorem, are going to work in our favor, but we have to be careful about them. Every extreme value occurs at a critical point where the derivative is either zero or undefined. that is not the same thing as saying that every critical point is an extreme value. When we're talking about conditions in mathematics, we often use the phrases necessary and sufficient. This is a necessary condition. If this does not happen, if we don't have a critical value, then you can't have an extreme value. It is not a sufficient condition. Knowing that you have a critical value is not enough information to then conclude that you have an extreme value. Right? So that subtle distinction is very important in this process. But we now have the tools we need to find a relative extrema. And in fact, we also have the tools we need to find an absolute extrema. We'll look at relative extrema on their own a little bit later. For this video, I'm just going to focus on absolute extrema. Because when you take a closed interval, it turns out that there's one other thing that can happen. The endpoints themselves are an oddity. Because if you think about our function that we've just been talking about, depending on how you cut off your critical values, or I'm sorry, depending on how you cut off the endpoints of the interval, it could be that you cut off right before an relative extrema, in which case the relative extrema is outside of the interval, and you just get as high as possible. It could be that you're continuing going indefinitely, and that's just the highest point at the endpoint, and the function would keep going, but you've cut it off. Or it could be that you have a relative extrema in the middle of the function. All right, so that still gives us a finite list of values to check. So if I'm looking at a particular function, let's try f of x equals x over x minus 2 on the interval between -1 and 1. All right, this is a rational function, so taking the derivative is not exactly pleasant, but as rational functions go, this one's not too bad. Derivative of the numerator is 1 times the denominator is x minus 2 minus the numerator, which is x, times the derivative of the denominator, which is 1, all over the denominator squared. We're looking for critical values. That means we're looking for places where f prime of x is equal to 0, in this case, there's no solution. We're also looking for cases where f prime of x is undefined. In this case, that's when the denominator, x minus 2, is equal to 0, which means that x is equal to 2. But we only care about what's happening on the interval from -1 to 1. Because this is outside the interval, we don't have to think about it, and we only can worry about those two endpoints. Right. With that, I'm going to set up a table. And on the table, I put in my endpoints. I would also put in any critical values that fall inside the endpoints, but our only critical value is outside the endpoint, so we don't worry about it. Then I evaluate the function at each of these points. f of negative 1 is negative 1 over negative 3, which is positive 1/3. F of positive 1 is 1 over 1 minus 2, 1 over negative 1, which is negative 1. And the biggest value happens when x is negative 1, and the smallest value happens when x is positive 1. All right, let's take a look at one more. This time, let's take a look at f of x is x cubed plus 3x squared minus 9x plus 27 on the interval from negative 5 to 5. We'll start by taking the derivative, which is going to be 3x squared plus 6x minus 9. And we're looking for places where this is either 0 or undefined. It's a polynomial, so it's never undefined. So we're going to look just at places where this is equal to 0. All right, solving this equation is not too bad. It's a quadratic equation. I notice in this case that all of my coefficients are multiples of 3. I could use the quadratic formula, but this is a pretty easy one to factor, so I'm going to go ahead and go about it that way. This is going to be x plus 3 times x minus 1, which means that x itself is either negative 3 or positive 1. And with that, I can write out my table. My endpoints have to appear on the table, negative 5 and positive 5. And the critical values that fall inside those endpoints also have to appear on the table, negative 3 and positive 1. And then we evaluate our function at each of those points. Right? Negative 5 cubed is negative 125. Negative 5 squared is 25, times 3 is 75. 9 times 5 is 45. All right, so negative 125 plus 75 is negative 50, plus 45 is negative 5, plus 27 is 22. Negative 3 cubed is negative 27. 3 squared is 9. 9 times 3 is 27. 9 times 3 is 27. Right? Negative 27 and 27 is 0. And then 27 and 27 is 54. One cubed is 1. 3 times 1 is 3. Minus 9 times 1 is minus 9. And 27. So we have 1, 3, minus 9, which is minus 5, plus 27, comes out to 22 again. And then we try 5. 5 cubed is 125, plus 75 is 200, minus 45 is 155, plus 27 is 182. All right. This particular function achieves its minimum at 2 separate places. It achieves the maximum at x equals 5, and then it achieves the minimum twice. I'm sorry, I wrote that upside down. I would like you to take a look at the function f of x equals x plus 1 over the square root of x on the interval from 1 to 5. And once again, the instructions here are to find the extreme values, the maximum and the minimum of the function on this interval. See what you can do with that one, and I'll see you in the next video.